So talking about magnetic circuits, we know what reluctance is. So our reluctance, we were drawing like this. Our reluctance, we were drawing like this with a little fancy R. And our reluctance had the units. So reluctance is how reluctant a material is to establish that magnetic flux. And that had units of inverse Henry or amp turns per Weber. And that's how reluctant this would be to establish a magnetic flux in, let's say, a magnetic circuit that looks like this. It's got a ferromagnetic material, and then in the ferromagnetic material, there are some coils here. There are n number of coils that are causing a flux to be established, and the flux, we know our properties of magnetism are going to have the flux sit comfortably inside here when, because it's a ferromagnetic material, when Fm is induced. So now that reluctance was about opposition. So it's opposing these flux lines. These flux lines are here. It's opposing these flux lines to be developed. But sometimes it's more convenient to think about the opposite of reluctance. So permeance means it's sort of how welcoming, how happy it is for those magnetic flux lines to be permitted to be established in this this magnetic circuit. So permeance, I like to draw it with a fancy P, just like we draw the fancy R like this. And I put an M for it's to do with magnetism, right? So the permeance is just the opposite or the inverse of that reluctance. So it's 1 over Rm. It's the inverse of that reluctance. And if reluctance was 1 over Henry, then Henry is the unit for permeance, or it would just be the Webers that were induced in there over the amps that induced it. And remember, we sometimes add a turn here as add turns here as non-official, not an SI unit, but it reminds us that the number of amps in each coil was multiplied by the turns, which induced these magnetic field lines in this material. So all we have done is we've taken reluctance and we've turned it upside down. We've looked at the inverse of it and we say, how permeant is this material? So that's what our formula is for permeance. However, so this is permeance. However, that's a little bit useless because, of course, a large magnetic circuit is going to be really, really permeable. And of course, a small one is not going to be permeable. So now let's look at this small magnetic circuit and this very, very large magnetic circuit. And if I think, and there's coils on here, and since there's coils on here, there's going to be, some flux induced in here. So I think, of course, this is more permeable, right? Of course, there's going to be more lines of flux established in a larger magnet, usually, like probably. But if I wanted to compare these materials and say which one is actually the more permeant of materials, so actually the most welcoming of established flux per material. So this is material A, and this is material B. And I want to say, is this one really more welcoming or is this one more welcoming? Is it more permeable or is this one more permeable? Because permeable means welcoming of that established magnetic flux. Well, I need to do this thing again called normalizing. And normalizing means I'm dividing by something. So in this case, I'm going to divide by the unit length. Let's look for a moment, do a little bit of an aside of what normalizing means. And let's just remember what normalizing means. It means comparing something to a standard. So comparing fairly. So my example is that we go into a grocery store and we see a box of cereal, and it's a small box of cereal, but it also has a small price. And then we see a large box of cereal, and it's large, but it has a large price. So are these equivalent to each other? We need to compare these fairly. So we don't just go and we say, oh, this one's cheaper, therefore it's a better deal, right? That's not comparing fairly. They're different sizes. I can't say, oh, this one is better at establishing flux. This one is more permeable or it has more permeability. It has more permeance. I can't say that that's better just because it's bigger, right? It's not fair. It's not a fair comparison. So um, we need to make a fair comparison over here when we're shopping, right? It's a fair comparison to say dollars per kilogram or dollars per gram or whatever is fair. So we've normalized that. And over here, what is fair is, what is fair is actually to normalize. What's fair is actually to normalize per unit length, because it is that length that helps that get established. So here I'm going to say per meter of length. And I'm going to take the same meter here. And I'm going to say, well, what is the permeance or inverse of reluctance? What is the permeance? Permeance per 1 meter. And what is the permeance? Permeance per 1 meter here, per 1 meter length. Then now it's a fair comparison. Well, per meter, this one might be massive compared to the other one, even though it was a smaller looking circuit. So that's all we've done here. But true to magnetic circuits in general, true to magnetism, we decided to give that its own unit. Its own unit. So now we have permeability. Permeability. Permeance needs to be calculated per unit length, which is normalizing, and cross section, So it has to be per unit length and times that cross-sectional area, which is actually a volume per unit length, and cross-sectional area. Length times cross-sectional area is actually a volume. So now we're looking at this whole volume in here, and we're looking at this whole volume in here. So permeance needs to be calculated per unit length and cross-section, and this is called permeability. All right. So what we have done actually, so we're actually going to look at this per area. Per area. We're actually going to look at this per area for a given length. For a given length in meters. So we have permeability is equal to the permeance we had before, PM, times a ratio, that should be a soft bracket, a ratio of length over area. And that's our normalizing. Which is going to give us Weber per amp turns times meter over meter squared, which will give us, if we were to simplify those units, we have a meter and a meter squared here. So our units are going to be Webers per amp turn meter. Weber per amp turn meter. And we have to remember that a Henry is a Weber per amp turn. So it's a Weber per amp turn times meter are our units for permeability. So this sounds complicated, but really all we're doing is we're saying, let's call a new thing permeability, which we do often when we normalize concepts. So for example, conductance is normalized per geometric shape, and it's called conductivity. So it is just going to be our regular permeance multiplied by our factor of length and over area. And here we go. If we remember that permeance is 1 over reluctance, then it is length over area times 1 over Rm, just because of the relationship between PM and being the inverse of Rm. So that's what permeability is. And it is now in amp turns per meter, but don't forget that it was multiplied by meter and divided by meter squared.